Okay, good morning to everyone. I'm Ian Bailey, the Network Product Manager here at Solutions PT, and with me is our Network Specialist, Ed Stanier.
Good morning, everyone.
So today we're going to discuss Ethernet redundancy protocols for OT networks, a little administration at the start. Questions throughout the webinar can be posted via the chat box, and we also have a Q&A at the end. But to start, I'll just give a little bit of background on Solutions PT. As many of you know, we've been working in the OT market for over 30 years. We're best known for Wonderware, but we also provide a lot more than this. And as you can see from the partners at the bottom of the screen, picking a couple out, we have Clarity. We provide a continuous threat detection, visibility, and monitoring software, which is very exciting for us, and I hope you'll look out for it in future webinars. I'd also highlight Hirschman, a leading light of industrial networking, and they're also referred to quite a lot during this webinar. So now I'll pass you to Ed, who's going to review the agenda.
Thank you very much, Ian. Okay, so the agenda for today. We're firstly just going to have a little look at why redundancy protocols are so important in an OT network. So we'll look at why we're kind of discussing this and why this is such a big topic in the first place. Then we're going to kind of dive into 3 different redundancy protocols themselves. The first one, spanning tree, which a lot of you may have already heard of and come across. This is kind of the industry standard of redundancy protocols. We'll look at Mrp, Media Redundancy Protocol, which is a little bit more geared specifically towards OT networks. And finally, we'll look at quite a specialist one, Parallel Redundancy Protocol, PRP. And then we'll kind of finish off with a little comparison and just a bit of guidance on kind of how you could best choose, the best redundancy protocol for your network.
Okay, so we've looked at a number of OT networking concepts in our webinar, and this is obviously a very specific element. So how do the protocols sit within that overall framework?
Yeah, I mean, this is kind of a key element really towards the planning and the ongoing kind of maintenance of a network, because your redundancy protocol is what will govern how much downtime you may or may not have. And that's kind of something we'll make a big point about, is that the whole point of these redundancy protocols are to minimize that downtime. So really they play into the kind of whole topology of a network, and they really do have a lot of importance when it comes to the uptime of your network and obviously of your overall production. Okay, so we're just going to have a look first at the importance then of these redundancy protocols, and basically what it comes down to is avoiding single points of failure. So your single points of failure, obviously points in your network where, should they fail, your network will experience downtime. And when your network experiences downtime, then you will have disruption to your production parts of your process, and it's obviously something that we really want to avoid. So redundancy protocols are like a very easy and cost-effective way for us to improve our uptime and to reduce these single points of failure, which is it's a kind of overall goal. When we're designing a network and we're looking after a network, we want to have as few single points of failure as humanly possible. And these redundancy protocols are a great way to stop us from having easy points of failure. And we'll kind of have a look at a couple of examples where we do have single points of failure, and then examples where we don't, and ways in which that's going to obviously help our uptime a lot. Now, it's not just failures within cables, hardware failures, that kind of thing that these redundancy protocols will help us with. It's also going to help us with things like accidental connections and disconnections of uplinks. And this is something that people may have come across before, where perhaps slightly less experienced engineers is plugging network cables between 2 switches. They may inadvertently cause a broadcast storm and inadvertently bring the whole network down. So this is something that's going to kind of help us with that as well.
So Ed, we as an organisation, you as an individual, we see a lot of different industrial networks. But how often would you say you come across instances of network failure or even accidental connections of uplinks?
Surprisingly quite a lot, and the thing is, if a network is running on kind of a bunch of managed switches and we have a redundancy protocol in place, then things like these accidental connections, they're going to go completely unnoticed because everything is going to run as normal. So I have seen instances where unmanaged switches are being used and someone will accidentally connect, let's say, a kind of bus network back on itself, so 3 managed switches connected back together, and without obviously understanding the implications of what they've done, they'll inadvertently bring the whole network down. So you'd be surprised, actually, it can quite be a common occurrence, especially for perhaps a slightly less experienced people when it comes to networking, who find themselves in comms room and, you know, they're trying to get connectivity to somewhere and they end up plugging cables where they shouldn't do. So with that in mind, let's have a look at this example here. This is just an unmanaged switch network. So let's assume we've got 3 switches here. They're all unmanaged. The uplinks between them, regardless of whether they're copper or fiber, the same kind of principle applies here. Now, in this example here, we cannot have any redundancy. So we can't connect switch 1 back to switch 3 and form a ring. We just can't do that with unmanaged switches. That's something we'll talk about in a minute about why managed switches are so important, and this is a prime example of this. So let's just assume we've got this unmanaged switch network here, 3 switches. Now, let's look at these 2 scenarios here. The first one is kind of what I've just mentioned, where someone accidentally connects switch 1 to switch 3, and I have seen this happen before. Someone thinks they're doing a good deed by adding a bit of redundancy to a network, but obviously because we've got unmanaged switches and because of how Ethernet works, that will cause a broadcast storm and that will bring your entire network down. Nothing will work. Everything will be completely unresponsive at a network level. Also, the second example there underneath, where we've got a failed link between switch 1 and switch 2, that's the same kind of issue there. The disconnection between those 2 means that we have a lack of connectivity between switch 1 and switch 2.
So there's clearly not much redundancy there, or no redundancy there. But would you say that unmanaged switches are fundamentally bad? And how often do you come across them in industrial networks?
Now, when I say they're fundamentally bad, I suppose I should clarify that a little bit and say that they are bad in certain parts of a network. So in the kind of main topology, you want to avoid unmanaged switches at all costs. Now, they do have their place in the network, and perhaps the best scenario for installing a managed switch would be a kind of spoke level of a network. So let's say you've got your main network, and coming off the network, you've got a spoke that goes to a certain production area. You may have a few PLCs, a few automation devices down there. In that scenario, it's not such a bad thing having an unmanaged switch. It's a nice, quick and cheap way for us to provide some extra port capacity, and we don't necessarily have to use the managed features at that level. We just want some very basic connectivity. So in that instance, unmanaged switches aren't such a bad thing. The only issue I would say at that point, and this will kind of bring me on to the 4th point down here, is the lack of visibility of them. We'll come on to that in a second, but just going back to those 2 scenarios, the same result is that we will have downtime. And the other issue there is that we then have to troubleshoot why we've got the downtime. So chances are the first thing that will happen is you'll notice that parts of production will stop working, but we then have to troubleshoot why that's happened. Someone will have to go into the comms room, investigate why we've had disconnected cables, why we've had accidental connections, that kind of thing, and that's all time wasted where production's down, and obviously that's a very bad thing for us. Now, would we have had a redundancy protocol in place there, then neither of those scenarios would have caused this downtime. Everything would have worked the same as before. We wouldn't have even noticed a single blip in the network.
With a managed switch.
Exactly, yeah. And that's another reason why managed switches are so good. So the example of the unmanaged switches, whilst they do have their place in the network, we have a serious lack of visibility of them. And that's why monitoring and logging are such a good thing. So for example, using something like Hirschman High Vision, we've got complete visibility of a network, and assuming we've got managed switches throughout, we can see the health of the switches, we can see if they're up or down, and we can see if the links are disconnected between them, that kind of thing. So we've got 100% visibility of the network and the health of it.
So it sounds like this monitoring is fairly vital too.
Absolutely. Yeah, absolutely. Yeah, if you want complete visibility of a network, so every device and every piece of hardware on the network, then yeah, absolutely, you need some kind of monitoring in place. And it doesn't have to be a complex monitoring package, like I mentioned before. Hirschman High Vision is a nice, easy to use kind of software suite that will give you nice visual representation of kind of health of a network. Okay, so we're going to start now by looking at spanning tree. As I say, a lot of you may have come across this before. This is a kind of industry standard for a vast majority of IT and OT networks. And the reason it's the industry standard is mainly because this is supported by every single major network hardware vendor on the market. So any managed switch that you will come across, there's a 99.9% chance that spanning tree will be installed on there, and in a lot of cases enabled by default. So we're just going to have a little look at the basics of it, and we've got a nice simple topology here. We don't want to make this example too complicated. So this is just a kind of basic ring. We've got 4 switches here. Now, the way in which spanning tree works is we have a root switch, or a master switch, if you will, and this is essentially the switch that is kind of in control of the topology, and each switch that is not a master switch or not a root switch will then have a single path to our master switch. Now, in this topology, we've got a nice simple ring here, and because of that, we only need to block a single port on here. And you can kind of see that with the top link there between switch 4 and switch 3, that's where we've got our blocked link. Now, we can define which of these switches becomes the master or the root, and that's all done by a priority, so a value that we configure on each of the switches. And the lower the priority, the better chance that switch has of becoming the master. Now, in an instance where all the switches have got the same priority, what happens is spanning tree will use the lowest MAC address to determine which switch becomes the master. Now, in this scenario here, like I say, because we've just got a single port that requires to be blocked, everything else is a normal operational port, operational uplink, and traffic will flow in that direction. So in this scenario here, let's assume switch 4 wants to talk to switch 3. It has to go to switch 2, to switch 1, and then to switch 3, because that port between switch 4 and switch 3 is blocked. So just to go into a little bit more detail about ports that are blocked, spanning tree puts a kind of big emphasis on the bandwidth of the uplinks. So, for example here, let's assume we've got gigabit throughout our ring, except between switch 2 and switch 1, which is 100 megabit. Now, logic would say that if switch 1 is our root switch, switch 2 wants to talk to switch 1, it just has to go down that link. But because that is only 100 meg, and because of how the spanning tree algorithm works, spanning tree determines that the quickest path is actually to go from switch 2 to 4 to 3 to 1. Now, these are things that can be configured. We can configure port priorities and things like that, but the default behavior of spanning tree is to perform in this way. So 100 meg links are considered very slow, slower latency, that kind of thing, and that's why we would choose that path there. Now, the actual purpose of spanning tree is to give us the redundancy. So in this instance, should one of the other links fail, one of our 1 gigabit links was to fail, then our 100 meg link would become active. So obviously we would still have connectivity between all of our switches on the ring, and we don't have a single point of failure anymore. Any one of those links can fail, and providing it's an active link, then our block link will become active, and it will start passing traffic through. Now, I mentioned obviously the monitoring before. If we had monitoring in place on the network, then we'd be alerted to all these things. If a link fails, if a link comes up, it's all stuff that we would have visibility of. So the question is, why use spanning tree? And I guess the main reason is because it's compatible with all vendors and also cross-vendor compatible. So let's assume we've got a network of various different vendors. We've got some Hirschman, some Cisco, some Juniper, some Netgear. We've got it all thrown in there. Spanning tree will happily coexist there on the network. It's an open standard protocol, so the same rules apply regardless of the vendor. So it's great for networks that have kind of evolved over time, haven't kind of been designed with a single vendor in mind. And although spanning tree can be extremely complex and there's a great deal that can be configured on it, by default it will operate fine. It will operate and give you what it needs to give you, which is the redundancy. So it may not necessarily be in the most optimal way, but out of the box you can plug a bunch of spanning tree switches together and it will work absolutely fine. One of the other good points is its flexibility when it comes to the topology you've got. So there's plenty of room for error if you were to connect additional redundant links, which we'll have a look at in a second. And not only that, one of the most important features, which is a big topic nowadays, is cyber security. So spanning tree has got a bunch of security features that stop people from kind of potentially exploiting it.
So it all sounds good for spanning tree. Are there any issues that you come across with it at all?
Kind of, yes. I suppose one of the main ones being that if you were to leave spanning tree with all the defaults on, you were just going to leave it alone and let it kind of configure the network by itself, it may not be in the most optimal way. And I have seen instances in big networks where spanning tree using the lowest MAC address to determine which will be the master switch is a bad thing, because a lot of the times the lowest MAC address is potentially the oldest switch. So I have seen an instance in a 15 to 20 switch network where a 25-year-old switch, 10 meg switch, got elected as the master because it had such a low MAC address. The network did run fine, although very sluggishly. So in that instance, you kind of have to be a little bit aware of the topology you've got, and if you are going to configure one thing and one thing only with spanning tree, it will be deciding which is your master switch. You don't have to get into the finer details of how a spanning tree works and configure port priorities and all the complex things. Just decide upon which is going to be your master switch, i.e. your most powerful, most centrally located switch, and then that's it. You can leave it alone, it will work absolutely fine. And this is just a little scenario of another reason why spanning tree is so flexible. We could have a topology like that, a ring with lots of interconnected links. Spanning tree will just take care of them. You can plug in as many as you want. Spanning tree will just block them. It's not an issue. You won't notice a single drop packet on the network. Spanning tree will determine their redundant links, and it will just block them. And you could argue that you've got kind of a very high level of redundancy there. You could lose up to 2 or 3 links between your switches and still have connectivity. So if you did choose to have something like that, perfectly viable with spanning tree. So that brings us on to the second one, MRP, Media Redundancy Protocol. This is formerly Hyperring and originally developed by Belden or Hirschman. And this is, unlike spanning tree, only compatible with some switch vendors, in particular your industrial switch range. So Hirschman, for example, or the new Cisco industrial range also supports MRP. Now, unlike spanning tree, we can only run MRP in a ring or a multi-ring network. We can't do what we saw on the previous slide and have a bunch of interconnected links. So it's a lot more strict when it comes to the topology you've got. And one of the advantages and one of the reasons people use MRP is because it does technically offer much quicker recovery times should you have a link failure.
So why is MRP stricter than FTP in topologies it allows?
I mean, the reason for that is because of how simple MRP is to configure, in that when we go to configure MRP, we essentially choose 2 ports. So we've got an in-port and an out-port. So I guess the reason MRP was kind of developed was to provide redundancy for rings and rings only. So we've got a port in and a port out, and that's all we can configure. We can't then add additional redundant links, and that's the reason why it's strict. It has to be part of a ring or kind of a sub-ring, which we'll come on to in a minute. So again, same topology as before, and it does work in a similar way to spanning tree in that we've got a master switch. And again, this is something we can configure, or we can allow MRP to do this automatically. Again, if you were to kind of configure an MRP network, this is something you'd probably want to define yourself. At the very least, just say which switch you want to be your kind of ring master. And this is your media redundancy manager. Now, all your other switches in the network are known as media redundancy clients. And all switches will essentially send control frames around the network, talking to each other, constantly keeping track of the topology and constantly keeping track of the kind of health of the links and whether there's been a link failure. And then it's obviously up to the manager, the master switch, to enable a block link if you've got one that's failed on the network. And one of the things that MRP advertises is its extremely quick recovery times, which we'll come on to in a second. Now, before we do that, we're going to have a little look at a slightly more complex network. And should your network be of a kind of decent size, or should you find yourself having to expand it, then if you are using MRP, it still has to adhere to this kind of ring topology. So what's happened here is we've got our main ring, then let's assume we've seen some kind of growth in our production areas and we've expanded. We've then essentially added 2 additional rings to the main ring, kind of bolted them on. And the way in which this works is we've got these sub-ring managers, and they are essentially part of our 2 rings, part of the main ring, part of the sub-ring. And obviously the same principle applies. We've got full redundancy around our individual rings and technically around the whole of a network, but still it has to adhere to this kind of ring topology. We can't then go connecting links between the middle of our ring, because that will cause a broadcast storm and it will crash the network.
So this is slightly more complex than the spanning tree network we saw earlier. Are these sorts of topologies difficult to implement or manage using MRP?
It definitely becomes a bit more of a not a concern, but I suppose you've got to be a lot more aware of your topology when you want to implement this. So yeah, there's definitely a kind of additional level of complexity. You have to be absolutely sure that this is what your topology looks like. You know, a bit more planning has to go into where your uplinks are connected and that kind of thing. So really, this kind of topology is where you need to have a certain level of experience in the kind of networking field, or at least you know, someone who's able to properly map out your topology, map out your network, and ensure that it actually looks like this. Because, as I say, the consequences of connecting a link where you shouldn't do, unlike spanning tree where nothing will happen and it will just take care of it, if you're just running MRP, you will crash the entire network. You'll cause a broadcast storm and nothing will be able to talk to each other, and obviously that's an extremely bad thing, especially in a live production network. So with that in mind, this topology we're about to see here, it loads. There we go. This topology here is unsupported. We can't do that. That will cause a broadcast storm. Now, the only way we can get around this is by running MRP as well as spanning tree at the same time. So we run MRP for our kind of main ring, and then if we want an additional levels of redundancy, we can also run spanning tree between these kind of interconnected links. Now, obviously, that's additional configuration. There is technically additional overhead on the network. You've got control frames from both protocols flying around. So it's something that people would perhaps steer clear of. Obviously, if you have the kind of skill set within your organization of when it comes to networking, someone could happily manage this kind of topology and have both protocols running at once. But that's really the only way that you could get around this kind of strict topology set that MRP offers. So that brings us on to why we would use MRP then, and that really comes down mainly to the faster recovery times. So in a kind of standard, or at least a small to medium-sized network of up to 14 switches, MRP can recover in about 10 milliseconds. So should one of your uplinks fail, you've got about 10 milliseconds of delay before the network recovers. And generally speaking, you won't see a single ping being dropped should you have a failure on an MRP network. Now, obviously, with spanning tree, that's perhaps a little bit slow, and the other problem with spanning tree is the unpredictability. So depending on how your topology looks, depending on how big it is, you can be looking between half a second, or in some cases, a few seconds. And in a lot of instances, that's not an issue, but where you've got kind of more latency-sensitive networks, then you need that recovery time to be much quicker, and that's probably the main motivation for using MRP. The other thing is the configuration is really easy. I mean, you basically select your ring manager, you select which ports are part of your ring on each switch, and that's it. There's very little complexity when it comes to MRP. Unlike spanning tree, you've got although it will work fine kind of by default and with a minimum configuration, there is a great deal you can do with it, a great deal you can configure, and that can sometimes be a little bit overwhelming for people.
So is the quicker speed of MRP actually worth it in an OT network?
I guess this comes down to the requirements of your network and the requirements of your devices on there, because in a lot of kind of production environments, a second downtime isn't an issue. You know, PLCs will buffer data and that kind of thing, so really it's kind of unnoticeable in a lot of cases, but you may have instances where your, OT devices can't handle that kind of delay. They're very kind of time and latency sensitive, and even a second downtime is too much for them, and it will cause issues. And in that case, yeah, you would want to use something like MRP. So really, it does kind of come down to what you're running on your network, the kind of devices you're running, and how sensitive they are. So we'll finish off by just having a little look at talking about PRP, Parallel Redundancy Protocol. This is kind of the platinum standard of redundancy, if you will, which you'll see why in a second. This is the kind of polar opposite in terms of recovery times of spanning tree. It's a specialist protocol, and it's only supported by some industrial network vendors. And the reason it's so specialist is that it essentially offers you 0-second recovery. So this means there's absolutely a guarantee of no loss of data during a single network failure. We'll look at why it's a single network failure in a second. The problem is with PRP is that it's difficult and expensive to implement. It's ideal for environments where you've got absolutely no tolerance for packet loss. If you have to guarantee packets get round the network with 0 latency, then PRP is the protocol to use. So we'll look at an example topology here in a second when it loads. There we go. And the way that PRP works, and you can probably already see why it's so expensive to implement, is you essentially have 2 physically separate networks, completely separated from each other in every aspect. So not just the cabling, but the hardware itself. You've got 2 kind of physical mirror images of your network. And the way it works is, in a kind of native environment, your PRP devices, so your PLCs and your other automation devices, will have 2 network cards, one connected to one network and the other connected to the other. What essentially happens then is every frame they send out will be sent out twice, once down each network. Now, the receiving device is configured in the same way. So in this example, we've got our server at the top, also 2 network cards, one into each LAN. It will receive both frames. It will look at the control information on the frame to determine what frame this is and if it's a duplicate, and obviously the first one that arrives will be processed, and the second one, which will arrive ever so slightly after, will be dropped. So this allows us for an entire network to fail.
Okay, so you can see that there's obviously more equipment, but also you've got to have a PLC with 2 network connections. So what do you do if there's only one?
Yeah, that's a very good question, and obviously that would be a kind of no-starter for a lot of people because, yeah, you're right, a lot of PLCs won't have 2 network cards, or perhaps some will, some won't. Now, there is a workaround for that, which brings me nicely onto the next slide, and that's by using what's known as a red box, or a PRP proxy. And essentially that is a network switch that understands the PRP protocol and will relay the PRP messages on behalf of single port clients. So in this instance at the bottom there, we've got 3 PLCs. They've only got 1 network interface. So they would connect into our red box, our PRP proxy, which would then relay those frames to both networks, and our end device would receive them in the same manner. Now, obviously, in that instance, we've still got the single point of failure on the PLCs, but after that point, we are sending 2 copies of the same frame around both networks to the end device.
It prompts a similar question, though, doesn't it? In that you look at that topology and you say, well, what if the red box fails?
Yeah, which is a very good point. And actually, in reality, that red box would most likely be a pair of stacked switches. So although that is kind of represented on the diagram there as a single switch, most likely what you'd have there is 2 switches in kind of stacked configuration. And obviously that would allow us still for a switch to fail and the other one to carry on as normal. So why would we use PRP? And really the only answer to that is when you've got absolutely no tolerance for packet loss. Because excluding losing both networks physically, so a complete disaster where everything's just disappeared, PRP will guarantee that that frame still gets around the network. You would have to lose an entire network. So there's a lot of tolerance there. It's a very, very, very unlikely scenario that both networks are going to kind of stop working at the same time, and obviously that's why PRP is at the other end of a scale and allows us for such a high level of redundancy. And obviously recovery time, it's instantaneous. Both frames have been sent at exactly the same time, so we haven't got to wait for our network to reconverge or anything like that. The frame on the other network will be sent round at line speed. So, we've not got to worry about any downtime, any recovery time or anything like that. But obviously the big issue here is the cost and the complexity. So if you've got a decent-sized network you want to introduce this in, it's going to become very expensive very quickly. And also the protocol itself, if you want your end devices to be able to read PRP packets, you've got to think about the drivers and that kind of thing, so it can actually read the control information.
So we've looked at it a little bit as we've gone through, but can you summarize how someone should go about deciding which type of redundancy protocol they need to implement?
Yeah, and I think this kind of table here covers it nicely, and really it all comes down to the requirements you've got on the network. And I suppose you can kind of categorize that into 5 different things. You've got your recovery time there, and obviously going from left to right, you've got a spanning tree, which is unpredictable. It could be 100 milliseconds, it could be a few seconds. You've got MRP, which generally speaking around 10 milliseconds, then you've got PRP, which is instantaneous. So, it all depends there upon how sensitive your devices are. Again, configuration, spanning tree, it does have complexity, but in theory it's a bit more kind of plug and play. You can plug it in and it will work and it will do what it offers, which is give you redundancy. MRP, nice and easy to configure as well. You've only got to decide which are your uplink ports and which is your master switch. PRP, very complex. You've got to think long and hard about your topology. You've got to implement it at the driver level as well, that kind of thing. And vendor support's a big one as well, because spanning tree, you could have a mixed network of lots of different vendors and it will work absolutely fine. With MRP, you've got to check your vendor compatibility. Like I say, only certain industrial switch vendors will support it. And PRP, obviously, is perhaps even worse in that respect, in that because it's more specialist, you'll find fewer vendors and perhaps you'll find it a lot harder to implement it at the end device level. Your topology consideration, that's something you really got to think about. What does your topology look like? Is it a ring? If so, nothing's stopping you from running MRP, and if you're comfortable that that topology is going to stay as it is. If yours is a little bit more complex, you've got a ring, you've got a bus here and there, you've got a connection from your bus to your ring, and it's a little bit more mishmash, so to speak, then spanning tree is probably the topology for you. You can have an unlimited amount of redundancy on there without having to worry about these additional redundant links, because spanning tree will take care of it. And then obviously with PRP, your complexity comes in that you've got to have 2 physically segregated networks. So you've basically got to duplicate what you've got on one network into a completely physically different one. So really just a finishing point, it all depends upon the environment that you have and how sensitive your devices are, because ultimately it will come down to the downtime. If a second or 2 downtime isn't an issue, which in a lot of cases it won't be, then spanning tree is probably your best bet. It's easy to implement, it's widely supported. If you do need a little bit of a quicker recovery time, then yeah, MRP is probably the way to go. And obviously, if we're talking kind of super mission critical environments where you've got absolutely no tolerance for any downtime, then you can look at PRP, but obviously be prepared to have a bit of a headache trying to configure it.
All right, well, thank you very much for that, Ed. I hope everyone enjoyed this discussion of Ethernet redundancy protocols. Alongside the products we mentioned earlier, we also offer network audit services and network training courses for those of you who need to know more to manage your OT network. And details of all of our products and services, alongside more networking webinars, are available on our website at solutionspt.com.